All right, in this video, we're going to continue with 3.1. We're going to look at some of the connections between functions, the f of x that we studied last time, and the graphs of the functions. So I'm going to start with an example to get this going. In this example, I want to describe a function. This one actually has a name. It's called the squaring function. Other names also, but it's defined by the formula f of x equals x squared. So a pretty simple formula. I can find values to build the graph by using a table where I'll have some x values and then y values that come from the function f of x, or we could just put x squared. We can put the formula in. My y values are from the function values in general, the f of x values. And so I'm just going to choose a few because I've done this before. These numbers will get the idea with these. If x is -2, f of x is -2 squared, which is 4. If x is -1, x is -1 squared, which is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. This gives me some points that I can use to build a graph of this function. With these x values and these y values, we could list this as a set. This is you've seen this a little bit. I'm not going to do this whole thing. It takes a long time to write. But these are xy pairs, -2, 4, -1, 1, 0, 0, and so on. I'm not going to finish that. That's not a very efficient way to write down a function. This graph is going to be a much better way because we're going to be able to not only use the points we have, but fill in some of the points in between. So my x values range from -2 to 2, -1, 1, and then the y values, lowest one is 0, but they do go up to 4. So that'll be enough to get these points. -2, 4 is here, -1, 1 is here, 0, 0, 1, 1, and 2, 4. And if you follow along with those steps, you'll have a good start for building graphs from sets of points. Now, to fill this in, I'm not just going to do lines. I know this function curves as it gets down toward the origin. And it kind of straightens out as it goes. The curve keeps going. We can't draw this whole thing because it really keeps going. Also, you can see there's a lot more points here than just those 5. I have a large picture of a lot of different points that satisfy this equation. For example, I could get x equals 1.5, 1.5, and square that. It's 2.25 or something. What's up? Okay, you can't come inside. Noah? Next, we're going to look at some examples of graphs and see how we can tell if a graph represents a function or not, because some graphs aren't functions. So what we're looking at here is called the vertical line test. And if you remember from the definition of a function, an input should have exactly one output. You can have different inputs that have the same output, but one input can't have different outputs. And this is reflected in the vertical line test. First of all, I'm just going to show you how to use it. If you want to read it, it's in the book. But it works like this. If I have a graph, say a swoopy, wavy sort of thing like that, and if I can draw a vertical line that hits it twice or more, that's not a function. If I can't draw such a line, in other words, if every vertical line crosses this graph once, here's a vertical line, crosses it once there, and there's nowhere on this graph that I can draw a vertical line that'll hit it twice. This is a function. And I'm going to label it that. There's some practice problems that you'll be able to do this. It's very quick. There's no computation involved in the vertical line test. Here's another example. Let me put some arrows on these to make them easier to see, the axes. Here's another graph that fails the vertical line test. So I can draw a vertical line here that doesn't touch the graph, or a vertical line here that touches it once. But the important thing is I can draw a vertical line that touches it in 2 places. So this is not a function. I have another example that's a little bit more familiar. This shape is a curve, a circle. It's a curve in the xy plane. But is it a function? It is not. For example, and how I like to do this, if you're just looking at them, don't draw in your computer screen or your phone screen. But if you're doing this on paper, you can actually draw a little line and circle a couple places where a vertical line touches the graph. And again, this is not a function. There are more examples on page 172. We're also going to look at, so the vertical line test tells us if a graph represents a function or not. We're also going to look at another type of test called the horizontal line test. But we'll come back to that. First, I want to give you what's called the library of functions, or library of basic functions. That'll give us some more variety on the shapes and the formulas that show up in functions very frequently. This is page 174. I'm not going to do all of these, but we'll get most of them because they're all fairly important. First, the simplest function is called the constant function. And a constant function has a formula, f of x equals c for some real number c. So no matter what x is, the value of f of x is c. F of 0 is c. F of 1 is c. F of negative 12 is c. F is just c. And the graph is, well, the graph is a little bit boring, but whatever that number c is going to be the y-intercept. You might recognize this. Y equals c is the equation of a horizontal line, and the graph is a horizontal line for a constant function. Another simple function, a function that has a very simple graph at any rate, is the identity. Put its name here. Identity function. Constant function, if you want. But the identity function has the formula f of x equals x, which means whatever I put into the function, I get exactly that out of it. And this one is potentially more flexible than some other functions. I guess this one too. If you put a hippopotamus in here, you get a hippopotamus out. f of 1 is 1, f of 5 is 5, f of cucumbers is cucumbers. Whatever you put in, you get the same thing out. Now the graph for us is going to be related to the xy plane and the real number line. So we're just going to put real numbers x in. If I put in 0, I get 0. If I put in 1, I get 1. If I put in 2, I get 2. If I put in 3, I get 3. Same thing. If I go the other way, f of negative 1 is negative 1. F of negative 2 is negative 2. F of negative 3 is negative 3. And you can see that these points all lie on the same, I would call that a diagonal line. The line y equals x, in other words. The next one we'll look at is related the absolute value function. And that formula, f for function, I call them all f, but this function is defined by the formula f of x equals the absolute value of x, which is actually, if x is a positive number, then the absolute value of x is just x, like the absolute value of 5 is 5. That's this half of the line from the previous one, from the identity. Whatever you put in, you get exactly the same thing out. And that graph over to the right looks like that same shape. But on the left-hand side, when x is negative, for example, f of negative 1 is the absolute value of negative 1, which is positive 1. Absolute value of negative 2 is positive 2. So, and it doesn't just happen on those whole number points. It's really a whole V-shaped curve. And I think we've seen a graph of the absolute value. Well, this is just looking at it as a function. All right. The next one on the list that I have is the one that we looked at first, the squaring function. Here they call it the quadratic function, and it is a quadratic function. It's just, there are lots of quadratic functions, and this is just the simplest. So I'm going to call it quadratic function, just like they do. Its formula is f of x equals x squared. Again, not the only quadratic function, but this is the simplest. And the shape, we saw that before. This is a pretty important vocabulary term. The shape, it's not a V, it's a U shape. And it's called a parabola. More on these later, but in the list, the next one is the cubic function. What I would actually call the cubing function, but it is a cubic function. It's the simplest cubic function. F of x equals x cubed. Now that graph is the upward swoop and the downward swoop. It's going up, it's increasing, but it's also scooped upward or concave up. The other part is not only, like if I go to the left, it's not only going down, it's scooped down. Now it is increasing. It's going up if I go left to right for the whole thing. It's just that the curve, the way it curves is different. And by the way, these two are the first that we've seen so far that are actual curves, that we would call curves rather than lines. The constant, identity, and absolute value they're made of lines. The absolute value is not one line, it's actually two pieces of two lines, but these are curves. The next one that we'll look at, I'm just going in the order they're going. This isn't what I would choose next, but this is a really important function, not just for working with functions and graphs, but also for understanding the relationships between large and small numbers. This is called the reciprocal function. And that's f of x equals the reciprocal of x, 1 over x. Now this graph, I'm not going to go into too much detail, but this is the first one we've seen that has a restricted domain. If you remember, the domain is the set of all the inputs for a function, and with this one, we can't use the number 0. If I plug in 0 for x, I get 1 over 0. That's not a real number. So we have to not have it at 0. We can get close to 0, though, much closer than 1 or negative 1. But let's start with 1. At x equals 1, 1 over 1 is 1. Now, let's go to 2. Next, let's get a little bit bigger. If I go to x equals 2, 1 over 2 is 1/2. That's half as tall. If I go to 3, 1 over 3, well, that's a third, even less than a half. If I go to 4, it's down to 1/4. And what's happening here is this curve, this part of the curve is getting closer and closer to the x-axis, never meeting it, but always getting closer. Now, if I go the other way, from 1, I mean, if I go to 1/2, for example, getting close to 0, for 1/2, 1 over 1/2, the reciprocal of 1/2, 2 over 1, which is 2. So if I do the reciprocal of a small number, I get kind of a larger number. Now 2 is not really large, but if I go in further to, let's go to 1/4. The reciprocal of 1/4 is 4 over 1, or 1, or 4 rather. And I'm just going to fill in this curve. You can see where it's going. It's getting closer and closer to the y-axis. The word is asymptote, and we'll look at that a little bit later in the semester, but it's going down and getting closer to the x-axis here. It's going up and getting closer to the y-axis here. This isn't actually going up. It's coming down, if I think of it as left to right. Now, let's do a little bit more on this side. Remember, I can't do 0, but if I use -1, the reciprocal of -1, 1 over -1, is -1. The reciprocal of -2 is 1 over -2, or -1/2. And the graph is doing the same thing in this direction that this piece is doing in this direction. The difference being that it's entirely below the x-axis. These are all negative y values. These are all positive y values. Now, it does something similar here too. 1 over -1/2 is -2. 1 over -1/4 is -4. And it's doing kind of the same thing with the y-axis, only instead of going up like that, it's coming down like that. So the reciprocal function is the simplest rational function. In other words, a function that's made of a fraction with variables. I'm going to skip the reciprocal squared function if you want to look at that, but it's not quite as important as this one. The two that we do need to look at, though, the last two, are the square root function, which is f of x equals the square root of x. And for the graph, I'm going to build points on this graph kind of quickly. I think that'll be enough. 1, 2, 3, 4. No, I'm not going to do all those numbers, but let's do the square root of 0. That's 0. And the square root of 1, that's 1. I'm going to skip a little bit, just 1, 2, 3, 4. The square root of 4 is 2. And I did that because it's easy to take the square root of 4, not so much with 3. We could go to, well, I ran out of board, but we could go to 9. Square root of 9 is 3. So it's increasing, it's getting taller, higher, larger y values. But it's going up slower and slower. And this shape is actually one that we've seen before. This is a parabola. This is the parabola x equals y squared. Not y equals x squared. That's the one we looked at before, the u. This is the top half of a parabola that opens to the right. So just the top half. The bottom half is it's negative square root of x. But if I have both of them, that's not a function. You can see that the vertical line test would say this is not a function. But this is only the top half of that parabola. So it is a function. And then one that's related to the square root function is the cube root function. And that's the function defined by the formula f of x equals the cube root of x. Now this one, I'm going to draw the graph a little bit differently. I want to get some larger numbers on the x-axis rather. So on the x-axis, we're going to go up to 1, 2, 3, 4, 5, 6, 7, 8, and -1, -2. -8. And we'll only need to go up a little ways and down a little ways on the y-axis because, well, you'll see from the shape of the graph. Let's start at 0 like we did before. The cube root of 0 is 0 because 0 cubed is 0. So 0, 0 is the point on the graph. The cube root of 1 is 1. 1 cubed is 1, so the cube root of 1 is 1. And I'm going to skip to the next cube, which is all the way up here at 8. 8 is 2 cubed. So the cube root of 8 is 2. And you can fill in the numbers similarly for that, just if you want to see it written down. The cube root of 8 is 2, so f of 8 is 2. Now going the other way, I'm going to get a few more points. The f of -1, or the cube root of -1 is -1. -1 times -1 times -1 is -1. So the cube root of -1 is -1. And also, -2, -4, -6, the cube root of -8 is -2. So I've got 5 points. I'm going to connect them, and the curve is kind of similar to the parabola. I don't know the name of it other than the cube root graph, but not the same, but a similar shape. This one actually has a very similar shape to the cubic function that we looked at a few minutes ago. It's short and wide rather than tall and narrow, but it is a similar shape. So that's a variety of functions, and you'll notice all of them pass the vertical line test. They are all functions. And